everybody. Welcome to the MathWizJohn Facebook Live, where today we will be going over some problems straight off the MIS-301 material coming on your future exams, or hopefully not the exam you just took today. Get you next time if so. We're going to be discussing one of my favorite things, the difference between the binomial and the hypergeometric distribution. Now, guys, we have made some updates to our situation here to make it a little bit easier for you guys to read. I know my handwriting can be a little bit tough. Always feel free, if you're looking and something looks a little confusing or my chicken scratch is hard to read, feel free to ask a question. We might not get back to you till the end of the session, but we're more than happy to answer it. Do give us some input. I'm going to be trying to keep myself out of the lens of focus for most of the session, keeping the writing large enough for everybody to view. We will be working on the glare. We appreciate your flexibility and your patience as we make sure that this is super valuable for you guys. So again, what we're going to be going over today, as you see on the board, is the difference between the binomial and the hypergeometric distribution. Again, this is going to be specifically relevant for people taking the MIS-301 statistics course. Also going to be relevant to your Stat 250 courses. If your teacher or your professor is feeling mean on that particular semester, it could be relevant to your Stat 119 courses as well. All right. Now, the thing that's tough when you go into introductory statistics is that you learn a lot of material, and it's hard to compartmentalize or tell the difference between those pieces of material. So the first difference that we are going to create today, we're going to draw out the entire sphere of statistics, and we're going to learn where our piece inside of it is. We have numbers that are described as discrete, or variables that are described as discrete variables. And we have variables that are described as independent. Right? Probably heard this word once or twice before. Right? Discrete numbers are finite, right, and do not have unlimited distance or values in between spaces. So something that's discrete is like number of people, number of trials. Anytime you're counting, where you can have one person, you can have two people, you can have 50 people, but you cannot have 50.45607 people. All right. So we have discrete and continuous variables is the other word here. Sorry about that. Continuous variables. Continuous variables, on the other hand, are infinite, across a spectrum. Things like weight and height are excellent examples of continuous variables. Now notice that your scale or your measuring tape does not have to have infinite possible decimals, but it is possible to be 120 pounds, it's possible to be 150 pounds, it's possible to be 180.678042971 pounds, making that measure a continuous variable. So both binomial distribution and the hypergeometric distribution describe discrete numbers only, right? So continuous distributions are described by our normal distribution. It's an example of it. The student T is an example of a continuous distribution. If you're using F-testing, oftentimes we're using a continuous distribution here, right? We're going to be focusing our discussion today on this side, discrete numbers. Remember, distribution is just a fancy word in statistics that describes a model, an algorithm, a picture, a graph, a means to solve a given problem, right? And what we want to focus on when we talk about distributions is the specific inputs, meaning the rules that a problem must abide by to use the distribution, and the specific outputs. What information is told to us when we make sure that our problem abides by the rules, plug in the numbers, and get an output, right? So we're going to talk about how to identify which distribution you should be using. Now, another thing besides being discrete and continuous that you could be in statistics is a variable could be independent, or it could be not independent, which is called dependent. Being independent means to have no affect on the probability. So two variables are independent if one variable occurring does not affect the likelihood of another variable occurring. My favorite example of that, I am a huge Minnesota Vikings fan. We have the Minnesota Twins cap in here. I'm always trying to run home and get my Vikings jersey on. Unfortunately, no matter how much I would like to believe that this isn't true, no matter how likely it is that I make it home on a given Sunday to get my jersey on or not, that event is independent from the probability that the Vikings win that football game. Dependent variables do have an effect. So what we're going to use to separate our knowledge here is the term replacement. So independent variables have replacement, while dependent variables do not have replacement. Be careful, the negatives and positives get back and forth here, right? Independent variables are described by the binomial distribution. So if you have a discrete variable and you're looking at independent trials, you would be using the binomial distribution to describe your sample or the data that you're looking for. However, if you have discrete numbers and you are looking at dependent trials, you would instead need to use the hypergeometric distribution. Sounds super fun, I know, right? So let's look at an example problem for how each function is going to be used. We'll get to learn all about the distribution itself as we do that. So a good problem for binomials, let's say you are a tennis player and you serve an ace on 22% of all serves. You want to know out of 20 serves, what is the probability of serving exactly 7 aces? Now 1, we know this is a discrete number. There's a discrete variable being described. Why? Because the variable in question is serves. Serving, which represents systematic trials. You can serve once, you can serve twice, you can serve 5 times, but try as you might, you cannot serve 10 and 1/2 times. It's not possible, right? This is a discrete number, right? We also know, mainly because they haven't told us that anything changes about the probability, right? If this probability is constant, this must be these are independent discrete trials. Every time the serve happens, there will be a 22% chance of serving an ace. The binomial distribution looks like this. N over x, p to the x, q to the n minus x. Now the way these variables are, that is n total trials, looking for x successes, with p the probability of success, and q the probability of failure, which in this case is 1 minus p. Now remember, success is relative to the problem. It doesn't have to mean a good thing is happening, right? You can define x successful events to be whatever x you're looking for. So if you're looking for failed exams, what's the probability that somebody fails their exam? You could define x successful events to be when you fail an exam. It's just the variable you're looking for. So don't get the language flipped up there, right? So what this is saying is that to solve this function, right, again, once we know that we are using the binomial distribution, we can quickly solve by plugging in our numbers. 20 trials, we are looking for 7 successful serves. 22% is the probability of success, and that needs to occur 7 times. The probability of failure is 1 minus 0.22, or 78%. If there were 7 successful events out of 20, there must have been 13 unsuccessful events. Plugging this as a series to your calculator will give you the final answer. Let's go ahead and get that written out real quick. Again, feel free, guys, if you need some guidance on how to plug these into your calculator. Lots of people do. Just feel free to shoot us a message and ask. The probability here is going to end up being 0.0765 rounded to 4 decimal places, so about 7% of the time. Now, what is this saying? 7% of the time. If this person were to serve sets of 20 serves, 7% of those sets of 20, they would have exactly 7 out of 20 ace serves. That's what this information is giving us. You can notice that a distribution is described by 2 things. The inputs that are needed. This needs n independent trials with p a constant probability of success that is unchanging. Those are the inputs. Anytime you have n independent trials that describe discrete variables with p a constant and unchanging probability of success, you may use the binomial distribution. What the binomial distribution will tell you is the chance, the likelihood of seeing x trials out of n, given p, the probability of success. Now let's compare that to our good friend, the hypergeometric distribution. Now, hypergeometric distribution says you have an old bag of Halloween candy with a total of 100 pieces of candy. And you know that 12 pieces have gone bad. So you select a handful of 15 candies, and you want to know the probability that you have exactly 3 bad candies. Everybody asks, when is statistics useful to your life? Can't get more useful than the expiration date on Halloween candy, guys. Come on. So, what is the likelihood? Now, first of all, why are we using the hypergeometric distribution? So, number 1, I'm going to say, is this a problem that describes discrete variables or describes continuous variables? These describe discrete variables. Why? Because we are looking at pieces of candy. Now, you can break a piece of candy in half, right? You can maybe break it into quarters, but it would be tough to tell me what does 1.38 pieces of candy look like. What is 1.49 pieces of candy exactly, right? So because those estimates are fairly impossible to create, pieces of candy are discrete numbers. Now, what's happening here, when you imagine what we really want to focus on is this, the selection process. We're selecting 15 candies. 15 candies are being selected, right? In a bag of 15 candies, what's the probability of 3 bad ones? Right? So these 15 candies that are being selected, the next level of process, every time we look at one candy by one candy, if you were to pull a piece of candy out from your group of 15, and you know that that was a bad candy, you're going to be holding one of the 12 total bad candies in your hand. So you may not know how many total were in your group of 15, but you do know that you just changed the odds by removing one. So this describes non-replacement, or there is no replacement happening in this situation. And so we can't use the binomial distribution because that means the probability is going to change from candy to candy depending on if the last candy was a good candy or a bad candy. So we're going to use this formula, right, which really we're just going to take the number of successful events the hypergeometric distribution is just a manipulation of our standard probability function. You can always find probability by taking the number of successful events or the number of successes divided by the number of total tries. You can always find probability like that. So again, keeping the same problem up, now what we want to do is we want to build ourselves a table. Right? We have two variables here. We have candies that were selected in your handful and candies that were not selected. And then we have candies that are good and candies that are bad. Now we know, making a little box here just to organize our thoughts, we know there's 100 total candies. We know that 15 are being selected, which means that 85 must not have been selected. We know that there's 12 bad total candies, which means there must be 88 good total candies. And we're interested in having 3 bad candies inside of our selection. So now we're going to use that to fill the rest of the table out. That means there must be 12 good candies inside of our selection. We must select 12 good candies. That means how many good candies are there that were not selected? 76, right? And then going either way, this is going to be the number 9 bad candies that are unselected. So now that you have your table, we're going to fill out a formula that looks like 3 combinations, 2 multiplying on top and 1 on the bottom. So, and again, I'm going to erase this so we make sure to have space and it's written effectively. Make sure to remember this, guys, right? Remember the numbers here. So, when we're looking to plug in, first let's start with the bad pieces of candy that must be selected, right? There are 12 total bad pieces of candy, and you need to select 3 of them in your batch. There are a total of 88 good pieces of candy, and you're going to be selecting 9 of them into your batch. Right? These functions stands for a number of possible ways. So this is the number of possible ways to have 12 good candies and pick 3. The number of possible ways to have 88 good candies and pick 9. And we're going to divide that by the total possible ways to have 100 candies and to pick 12 of them. Right? This is, again, number of ways to have 3 bad candies out of a total group of 12. Wow, or multiplied by the number of ways that you can grab 9 good candies from a total number of 88, divided by the total possible ways that you could draw 12 candies from a group of 100. So we're going to get very big number on top divided by even bigger number on the bottom. If you're getting the little E notice in your calculator, that's all good. It means multiply by 10 like scientific notation. Here the P equals 0.1197. Right? So always draw your box up for this. The more you do your work the same way, the easier the problems are going to become. You're going to get used to it, going to get some muscle memory involved. Right? This is the hypergeometric distribution. We knew we were using the hypergeometric distribution because why? we had discrete variables, pieces of candy that happen in 1s, 2s, and 3s, but not 1.7546s. And because these trials were dependent, the probability changed from trial to trial as you looked at candy to candy based on the last piece of candy you looked at. So we're going to do another example of both of these functions that help get the calculator involved real quick. So let's say now that we understand how the difference between these two functions work, what happens when we go back to our original problem, which was, remember, an ace on 22% of serves. And we're looking at 20 total serves. Let's say you're playing a very good opponent and you want to know what is the risk, what's the probability that you get 5 or less ace serves out of those 20. Now the difference here is that the binomial function operates differently when we're looking at a single point at exactly 5 or at several points up into 5. Now mathematically the way this would work so we can see it, here is how the probability of 5. 20 choosing 5, 0.22 to the 5th, 0.78 to the 15th. Then we want to add also what's the probability of seeing 4. That's 22% to the 4th times 0.78 to the 16th. Right, we'll just do one more. If you're staying along with me, great. Choosing 3 to the 3rd and to the 17th. So if you can see the pattern, what happens here, right? Here's the probability of 5, 4, and 3. We could add 2, 1, and 0, add all the values, and answer this question by hand. Most people find that a daunting amount of math. They don't want to do all this, right? So you actually can use a standard TI calculator. That is a calculator that looks like this. You can use the 84. You can use the 83. It's all good, right? It's actually set to solve these functions directly. So you're going to have in the section of your calculator that can be found by pressing the second button and then hitting vars, which should take you to the distribution window. You can find our good friend the Binomial Cdf. It's very important that this letter is a C. All right, the calculator can do the same function, and it has a PDF. It'll solve for exactly one place. CDF is for a distance. So what the Binomial Cdf function is going to do, it's going to ask you to input n, p, and x. And it's going to say out of 20 trials, with p, a given probability of success, what is the probability of being at x or less? It's really, really important to learn how your calculator works. We see a calculator function and we're like, ooh, I get to save so much work and time, right? And it's exciting, and we don't really learn enough about how it works. It's x or less. So this function is set to solve this problem exactly. We could go into the Binomial Cdf, bring the screen up, and enter 20 trials, 0.22 probability of success, 5 or less. Let's go ahead and all enter that together for practice. So you hit the Binomial Cdf. Here is what pops up onto your screen. Right? And then we're going to type in 20, 0.22, 5, close the window, and hit enter. And bada boom, bada bing, there is a 73.42% chance, or 0.7342 is the probability. So given that you have a 22% chance of having an ace on any single serve. If you serve 20 serves, what's the chance that you get 5 or less total aces? 73% chance approximately, right? Now, there's going to be a couple times where this gets tricky, right? What if it said instead of 5 or less, what's the probability that they get less than 5? Less than 5. Because the difference here, right? 5 or less means 5, 4, 3, 2, 1. Less than 5 means 4, 3, 2, 1. Your calculator is going to include the number that you plug in. So we would answer that same question, but with the probability of 4 or less than 5 is 20, 0.22, 4. Now, I know that probably seems pretty basic right now, guys, right? But that's the kind of things on your exam, just little tricks, little missing words that are going to make all the difference between things being easier or harder, right? The last thing is, what if they say the probability of being more than 6? And then we're going to do, finally, 6 or more. So more than is going to be 1 minus the less than option. So let's look at this. Here's the number 6, right? Things that are more than 6 are 7 and up, not including 6. Right? So what we're going to do to get this is 1 minus the probability of being 6 or less. Why? Because that's what our calculator can do. So we could do 1 minus the binomial Cdf of 20 trials with a 22% chance of success, 6 of them. What we're going to get is a solution that tells us the probability of being 7 or more, the opposite of being 6 or less. Some people like to get the number on its own, then do 1 minus the answer, or just do it all in one keystroke. Whatever floats your boat, as long as you get to 0.1301 at the end of the day. Alright guys, I know especially if this MIS class is your first statistics class, it is not the easiest thing to jump right on in. I know it looks really foreign, the scripting is unnatural, and it can be stressful. So we always got you covered, anything you need. It can be a lot more beneficial to see this done live and in person with one of our super awesome tutors. Feel free to reach out anytime you do need some extra help. I really appreciate you guys tuning in and look forward to seeing you next time. Again, we'll be doing this every Tuesday at 6 o'clock. Do feel free to send in any problems you want to see live. Accounting 201, Accounting 202, any of the econ classes, finance classes, BA classes, Math 120, statistics, whatever it is. Challenge me, guys. Send your problems over. We will be doing them free every Tuesday night at 6 o'clock. Have a great one, guys. Crush those classes, all right?